Hello everyone. So in today's class, we are going to learn dimensional analysis. Dimensional analysis. What is this dimensional analysis? First of all, how we can define it? So see here I am writing one definition. It is nothing but just a representation of any physical quantity in terms of powers of basic physical quantities. Okay, a representation of any physical quantity in terms of powers of basic physical quantities. How? Let's see ahead. Okay, so first let me explain which are the quantities and how they are representing in dimensions. So I'm giving you a small table. So only two parts we will take. So here I'm writing fundamental quantity. And representation in dimensional analysis. The first one is mass. It is represented by capital M in dimensional analysis. Okay. Next is length. It is denoted by capital L. Next is time. It is denoted by capital T. Next is temperature. So this temperature either we are denoting by theta or even by K. Next is electric current. It is denoted by I or A. Next, luminous intensity. And it is denoted by J. And amount of substance is there, but basically it is like a dozen. Okay, it is just amount of substance. So basically we are not using that. If it is used, sometimes they are using as a mole also. So I'm not writing that because it is just amount of substance. It is like how many mangoes? 1 dozen, 2 dozen, like that. So 2 mole, 3 mole, like that. So that's why that is just number. Okay. So basically these six physical quantities we are denoting like this, or we are representing in dimension analysis like this. So let's see one example. Then you will understand detail how we are going to use this dimensional analysis. So I am taking one example, concentrate so that you will understand, and I will give you some problem also to solve so that you will understand very nicely. Example. The first one, let us suppose find the dimensions of force. Find dimensions of force. Okay, listen carefully now. Force is F, you know, F is equal to what is formula? Mass into acceleration. Mass into acceleration. Now, okay, this is F. Now dimension started, so I am denoting or keeping it in a, I am keeping it in a square bracket. Now this mass is fundamental quantity, so mass is mass only into this acceleration is basically what? Velocity by time. Okay, what is this acceleration? Velocity by time. Change in velocity means what? Velocity only, velocity by time. So again I am taking this mass outside and this time also outside because time is also fundamental quantity. Left is what now? This velocity. Yes, this velocity is what again? This velocity can I write displacement by time? Yes. So this is I am writing displacement by time. Displacement divided by time. Okay, understood. Now come this side. See here. So dimensions of F is equal to. Now this is what? Mass. Mass is denoted by m in the dimensions. This is m. M. This is what? Time. Time is denoted by t. Okay, into displacement is what? Length. Displacement is nothing but length, so denoted by L, and this time is again denoted by t. So this is equal to m. This is L, and this is t square down, है ना? T square down. So this is equal to m power 1, L power 1, t power minus 2, and we should keep it in a square bracket. So these are the dimensions of force. This is what? Dimensions of force. Now how to read? So see here, read as. So I'm keeping this in the box. So read as one in mass, one in mass, one in length, and minus 2 in time. Okay, this is what dimension analysis is. Let's go back here. See, what is the definition now? Representation of any physical quantity. Representation of any physical quantity in terms of powers of basic physical quantities. See here. Now this is a force. This force is what? Any physical quantity. And how I have denoted now this? In terms of powers of basic physical quantities. Basic physical quantities is what? Mass, length, time, whatever I have given in that box. So 1 in mass, 1 in length, minus 2 in time. This is what representation of force is. And this is what dimensional analysis is. Is that clear? Understand? Okay. So let's solve one more problem so that you will understand better. So note down this first. Okay. So next, one more example. This is example number 2, and this one is example number 1. Okay, so let's move ahead. So what he is asking you, let's take dimensions of pressure or else momentum, whatever you want, you can take anything. So I'm taking angular momentum. Okay, what I'm taking? Angular momentum, or momentum first. So let's take first momentum, because it's Newton's second law you have learned already, momentum. So let's take this. So that is linear momentum. Linear momentum. So this linear momentum is what, Ray? Denoted by P, and its formula is what? M into V, which is equal to what? Mass into velocity. Okay, momentum is what? mv, that is equal to mass into velocity. Now mass, so I'm writing here as a mass only. Once you will get practice, then no need to write these words and all, direct you can substitute. This is velocity, so can I write like this? Displacement by time. Yes, displacement and divided by time, because velocity, velocity is what? The rate of change of displacement, or displacement per unit time. So now all are in basic physical form, or basic physical quantities, we can say. Mass is represented by capital M. Yes, displacement is represented by capital L. Divided by time is denoted by T. So this is equal to what? M L, and this is T power minus 1. So if you want to find, or what are the dimensions of momentum, are what? 1 in mass, 1 in length, minus 1 in time. Okay, so how you will read? How you will read? 1 in mass, 1 in mass, 1 in length, and minus 1 in time. This is what dimensions of linear momentum. Understood? Is that clear? How much easy it is? Yes? Let's move ahead. One more example. Example number 3. So I'm taking kinetic energy. What I'm taking? Kinetic energy. Kinetic energy is what? Half mv square. Now this half is constant. What is constant? This is one constant. This is just a constant. So we don't have any dimensions for any constant number. So let's move ahead, but I am neglecting now this one. Half is just constant. So this is m into v square. So this is equal to, this is mass, and this velocity already I told, displacement by time, and keep it in mind, whole square. This is very important. This is very important. Now this is equal to, mass is what? Represented by m, into displacement is what? Denoted by L, time is T, and don't forget to square it. So what you are getting here? M L square T power minus 2. This is what? Dimensions of kinetic energy. So I am just denoting kinetic energy as a E, and you should always keep in a square bracket, and this is 1. Now you know how to read. 1 in mass, 2 in length, minus 2 in time. Next one. Example number 4, here only I am doing. So this is work. Suppose we want to find dimensions for work. Work is equal to what formula? Force into displacement. Force into displacement. So therefore, work is denoted by W. W. Force is equal to what? Mass into acceleration. Into this displacement is displacement only. Okay. So short में लिख रहा हूँ. This is already dimensions of this. So what is this? M L T power minus 2, and this is displacement is what? L, because already we have found out here. If you will see here, you have already got this M L T power minus 2. Just I am substituting there. Yes, at the place of this force. This one, right? So direct this and this. So you are getting W is equal to what? M L square T power minus 2. This L and this L square, and this is L power minus 2. Okay. So you see now, work and energy both are having same dimensions. So keep it in mind always, energy, those who are same units, those who are same units, those who are having same units will have same dimension. So node point क्या है यहाँ पे? What is the node point? Keep it in mind. Keep it in mind. Now kinetic energy, joule, work, joule, potential energy, joule. So they will have same dimensions. The physical quantities, those who are having same units will have same dimensions. Right? Shall I write here? The physical quantities with same units will have same dimensions. Will have same dimensions. Keep it in mind. Okay. So I will give you some formulas later. You just note down that in the notes. Okay. Right. So that we can find out the dimension analysis. So I'm solving one problem previous year. This problem they have asked in JEE Main 2013. Okay. And every year they are asking one question from this. So you just make perfect your dimension analysis. Even in EMSET also they are asking. So don't, what you can say, neglect this topic. It is very, very important. Question is like this. Find or like this they have asked. The dimensional formula for permittivity of vacuum if M is mass, L is length, and T is time, and A is electric current. M is mass, L is length, T is time. T is time and A is current. Means what? Mass is represented by M, length is denoted by L, and time is denoted by T, current is denoted by A. So how to find now this? Okay, this is what the question is. Sir, we don't know this formula also. We are learning this first time. What is this permittivity and all? But this permittivity concept you are getting in second year, and for JEE mains you are having syllabus of first year and second year. Okay, so some formulas you have to learn now also, which I am going to give you. Right, I will send you some photos. Not an issue, but you just learn the method how to solve this. Now first, this is permittivity, so we need to learn this Coulomb's law. Okay, this is Coulomb's law. Coulomb's law is what? F is diagonal proportional to Q1 Q2, and this F is inversely proportional to square of distance between them. You know, in gravitation, at least you learn know this law of gravitation, M1 and M2. Yes or not? And this is R. Then F is diagonal proportional to M1 M2. Yes, and F is inversely proportional to R square. So this you have learned already. So same like that, there is one another law, but instead of this masses you are having charges, but here it may be force of attraction and repulsion, where in charges, but in masses always there is force of attraction only. So here it may be attraction or repulsion in Coulomb's law. So here you see like these charges will be there, which are placed in a vacuum, Q1 and Q2, and these two charges are separated by distance r. Then this force is diagonal proportional to Q1 Q2, and this force is inverse proportional to square of distance between them. So F is diagonal proportional to Q1 Q2 by R square, and this F is equal to, I am removing this proportionality sign and I am adding one constant, that is your 4 pi epsilon naught Q1 Q2 by R square. Okay, so how to do now this? You see in this formula already I told you this 4 pi is constant, so this is having no dimensions. So direct I am doing now. Can I do like this? F R square divided by Q1 Q2 is equal to 1 by epsilon naught. Check it. Is it right? Just I have searched one formula. Whenever he is asking any dimensional formula, you try to get the formula. Okay, as this is you don't know, but now I am telling you. But so many dimensional formulas you should know. So is it right? Check it once. I transferred this R square this side. So R square F is equal to Q1 Q2 by epsilon naught. Then again I transferred Q1 Q2 also. Or shall I do one more step? So see here, F R square is equal to Q1 Q2 by epsilon naught. And then this Q1 Q2 also I transferred here, and you are getting this step. Now I think don't have doubt. Right. Now take reciprocal. So I am taking reciprocal. So Q1 by Q2 divided by F R square is equal to epsilon naught. Now F dimensions we know. Okay. R means length, dimensions we know. Q1 and Q2 we don't know. Okay. So can I write, see here, I is equal to what, Ray? Q by T. You have learned this current formula, Q by T. Yes. Then Q is equal to I into T. Here at the place of big Q, you are having small q. So this is also what? IT. So Q1 is first charge, Q2 is second charge. So let's substitute now. So what you are getting here? IT for this Q1, and for this Q2 also IT only. But he is saying current you denote by A. Current you denote by A. So last we will substitute, not an issue. F dimensions also we know. F dimensions are what? M L T power minus 2 into R square means length square. So this is L square. This is what your epsilon naught. Let's move ahead now. Now what you got? I square t square divided by, down is what? You see, this L and this L square, what you are getting? ml cube t power minus 2. So you are getting here ml cube t power minus 2, which is equal to epsilon naught. Right. Now take this up with minus sign. Those which are powers at numerator, you keep it as it is, but those which are at denominator, which are plus, they will become minus, and which are minus, they will become plus. Just transfer it up. M power minus 1, this plus 1 will go up minus. L power minus 3. Next, this is t power plus 2, t power 2, and already here, already what is there? I square and t square, which is equal to epsilon naught. But current we should denote by a, because he is saying denote current with a, because sometimes they will say in the question I is equal to a, so let's denote with a, not an issue. So what we are getting now? M power minus 1, L power minus 3, this t square and this t square I am adding, so what I will get? T power 4, this is I am replacing with a power 2, this is equal to epsilon naught, right? And therefore dimensions of epsilon naught, I am keeping in the square bracket, epsilon naught is equal to minus 1 in mass, minus 3 in length, okay, 4 in time, and 2 in current. If you will get this option, you will get 4 marks. How many marks? 4 marks. How much easy this is? Yes, right? So solve like these problems. I will send you some photos. Just go through it. Note down in the notebook all that charts as it is, and go through once that formula. Okay, let's stop here. Bye for today.